Photography from aircraft, and more recently from spacecraft, has given man a new and unusual perspective of the planet he lives on. More important, overhead photography gives our nation the ability to keep a vigilant watch on its potential enemies. Providing the American eagle with a sharper and closer vision of its adversary's actions has long been an important goal of U.S. intelligence. Like the eagle's far-reaching vision, one of today's reconnaissance camera systems can photograph and resolve details from nearly 100 miles in space. It was a giant step forward in photographic technology. How this unique and unprecedented capability was achieved, how it helps to keep America informed, is the story you are about to see. A history of how this new and penetrating vision was given to Gambit, the eye of the eagle. As the Iron Curtain lowered in the 1950s to conceal Soviet military developments, we realized that eventually conventional aircraft reconnaissance over communist territories would become impractical for political as well as military reasons. We would be denied crucial technical intelligence data during a period when it was most needed. The urgency to develop alternate reconnaissance methods was underscored by the detonation of the first Soviet hydrogen bomb in August 1953, only 9 months after America's first H-bomb test. After that, it became extremely important to monitor Soviet progress in nuclear-armed intercontinental range ballistic missile systems. With the development of our own long-range missiles in the mid-1950s, we would soon have the means to launch Earth-orbiting satellites, bringing photo reconnaissance from space much nearer to reality. Our developing space technology would eventually provide the nation with the required intelligence collection systems. As early as 1956, a development plan was established by the U.S. Air Force for what would be a family of satellite systems to collect intelligence, including a high-resolution photo surveillance satellite. The Soviet launch of Sputnik 1 in October 1957 burst upon the world with an impact seldom achieved by any single event. We in the United States were quick to recognize the implications of Sputnik. This exhibition of Soviet rocket technology proved that they too possessed an intercontinental delivery system for thermonuclear weapons. For U.S. intelligence, the gathering of detailed data on this new and awesome threat became a task of the highest priority. During the 1950s, the high-flying U-2 spy plane, as the news media called it, provided much valuable intelligence data on an interim basis. However, as our need for information grew, so too did the lengths of these flights over the Soviet Union, culminating in the disastrous flight of pilot Francis Gary Powers during the first attempt to make a one-way traverse of Soviet territory in 1960. After that incident, President Eisenhower ordered there be no more aircraft overflights of the Soviet Union. However, that well-publicized event gave added impetus to the development of photo reconnaissance satellites. Under the cover of program WS-117L, the Air Force launched and operated Corona, a joint CIA-Air Force satellite program for wide area search. Corona depended on physical recovery of its film payload, which would not be achieved until August 1960. And there was Samos, designed to process its pictures in orbit and transmit them to Earth via radio. This approach provided rapid data return, but did not have the adequate resolution to augment the wide area search of Corona. What was required was a photographic satellite system with high acuity and resolution to provide positive identification and analysis of individual targets. Such a system would have to produce imagery equal in sharpness and definition to that taken from high-altitude reconnaissance aircraft, but do so from altitudes of 70 to 90 miles above the Earth. The groundwork for such a high-resolution system was laid while Dwight David Eisenhower was president. Dr. Frederick C.E. Oder, then an Air Force colonel and previous director of program WS-117L in 1960, recalls how the future system was envisioned and how it was initiated.
In 1960, as a result of the early success in Corona in film recovery from orbit, the need was seen to greatly improve our capability in this regard. For this reason, Eastman Kodak proposed a system which would have a focal length approximately 3 times that of Corona, with a significantly larger effective aperture, improved film handling, which would give the desired results. They did this in the form of an unsolicited proposal, which was given to General Bob Greer, who subsequently, in November of that same year, obtained the approval of Dr. Joseph Cherrick, Undersecretary of the Air Force, for the program, which then was commenced.
Under Brigadier General Robert E. Greer, the first director of the Secretary of the Air Force Special Projects Office, there came into being tightly contained procurement and program management systems unprecedented in the Air Force. Major General David Bradburn, then a major in the security section of General Greer's organization, explains why.
We had some special security considerations for the new program. We wanted to conceal military activity in space to the maximum extent possible. This meant then that the very existence of the new program was to be concealed from the outset, even from other government agencies who would normally be involved in this type of activity. Along with the existence of the program, we wanted to conceal the quality of the imagery that we were going to get, which was going to be better than anything previously planned or undertaken. The security objectives were all the harder to achieve because the SAMOS program had been conducted with considerable public visibility. So the problem was to bury the SAMOS program and not to have the new program show at all.
Not long after, the program took on a covert codename, Gambit, an opening move in chess in which a pawn or other piece is sacrificed. And it was a chess player, Colonel Paul Heron, U.S. Air Force retired, who came up with the name by which it became known. Colonel Heron recalls some of the requirements established for the proposed space camera.
It should be understood that Gambit was designed to fly at 90 miles altitude or lower. It is important to recall that one of the primary requirements for Gambit system was the vehicle positioning and stability, because these are keys to the ability to roll the vehicle, to apply the optical elements to targets of relatively small size. It is almost needless to call your attention to the fact that no matter how successful Gambit was in orbit, only true success could come through recovery of the final photographic tape.
The solution to the film recovery problem came on August 11, 1960, when Discoverer 14 was snagged in midair, the first aerial recovery of an object returning from space. It meant that physical recovery could, from then on, be performed routinely and securely. Mr. Les Mitchell, who directed early Gambit development at Eastman Kodak, explains the basic specifications of the camera.
One of the major challenges in the design of the camera payload was to assess the then current state of the art in such important technologies as optics, mechanics, film emulsions, electronics, space sciences. What was needed was an optical system to image fine ground detail on film from a fairly limited area. In practical terms, this meant a system with a ground resolution of about 2 feet.
The proposed camera payload consisted of a 77-inch focal length reflecting telescope with an effective aperture of f4, coupled to a strip-type aerial camera using 9-inch wide film. In addition to the camera payload, the first Gambit system consisted of General Electric's orbital control vehicle, designed to provide a stabilized platform in orbit, and GE's recovery vehicle, in which Gambit's exposed film would be recovered from space. The Atlas-Agena combination, having proved serviceable and reliable in the earlier SAMOS programs, was selected as the booster vehicle. Gambit's polar orbiting requirement dictated that Vandenberg Air Force Base on the central California coast be the launch site. But transforming this concept into an operational system would require intensive effort by all program participants.
One of the important engineering problems was related to weight. We had a weight requirement of 1,500 pounds for the entire camera payload. One of the major contributors to the weight is the primary mirror. This is an example of lightweight fused silica mirror construction. And if successful, it would reduce the weight of the primary mirror from over 200 pounds to 85 pounds.
Another proven space performer from the Discoverer program was being groomed for its role in Gambit. In a covert production area at Lockheed's Sunnyvale plant in California, the Agena D was being modified to serve as the second stage booster. This period in Gambit's history between program start and first flight can best be described by those who were actively engaged in it. Men like retired Brigadier General William G. King, Jr., who was Gambit program director during the first 31 flights.
All the people understood the priorities that were attached to the program and the basic job of demonstrating high-resolution photography. There's no question in anyone's mind, and every precaution was taken to minimize the risk in demonstrating at the earliest time high-resolution photography. Certain provisions were made to the hardware to minimize the risk and assure that high-resolution photography was returned at the earliest time. Therefore, to demonstrate that we could indeed perform high-resolution photography from space. Therefore, if we did have failure of the basic stabilization system, we could return the photography from orbit. No one misunderstood what John Greer had said when he said, get one good picture as early as you can.
For a program destined to achieve success far beyond normal expectations, Gambit had a decidedly negative start on the launch pad on the 11th of May, 1963.
In preparation for the initial launch, we were performing a standard procedure of a dual propellant loading of both the Atlas booster and the Agena vehicle. During this procedure, we did lose pressurization of the Atlas, and in the case of the Atlas, there is no structural integrity maintained if you do not have pressure. So during the procedure, the Agena and the orbital control vehicle and the engineering payload was unceremoniously dumped into the fire bucket of the launch pad. Now, in this case, there was no more than 2 weeks lost in the flight schedule. I think this is indicative of the preparation and the planning and the resources that were applied to being sure that high-resolution photography was obtained at the earliest possible time.
By July 12th, the first Gambit system was in the final countdown. After 3 holds for technical reasons, the long-awaited liftoff came at 13:44 hours Pacific Daylight Time. The midday launch time would provide optimal lighting conditions over most prescribed targets in the Northern Hemisphere. All phases of powered flight proceeded normally to insert the satellite in the prescribed polar orbit. Soon after, military and contractor personnel at the Air Force Satellite Control Facility in Sunnyvale, California, began receiving telemetry signals from the spacecraft on the first pass. Telemetry returns from the vehicle indicated that all systems were functioning well. Orbital corrections were computed and subsequently transmitted to the spacecraft. On the 5th, 6th, and 7th orbits, Gambit's camera was turned on for several monoscopic strip exposures. On the next 2 passes, several stereo pairs were exposed. Following additional monoscopic exposures, photography was terminated because of a vehicle instability problem. On the 18th orbit, Lifeboat, the backup stabilization system, had to be activated to achieve capsule separation and recovery. After operating in orbit for a little more than a day, Gambit's exposed film was cut and sealed in the recovery capsule for re-entry. Recovery aircraft from the 6594th Aerospace Test Group, located at Hickam Air Force Base, Honolulu, snagged the descending parachute using a special air recovery device. Once caught, the capsule was reeled into the aircraft and flown back to Hawaii. General Greer's healthy respect for the unpredictable had proven sound. It was only by the inclusion of redundant systems that the first Gambit mission had achieved success. Though some problems were encountered with focus and image motion compensation, some ground objects 5 feet across were clearly recorded on portions of the film.
I think we have to keep in mind that in the Gambit program, it was necessary to perform operational missions during the period that you were really developing all elements of the program. Although the general nature of the program remained somewhat development throughout the 38 missions that were flown, it was an operational program, and operational high-resolution photography was obtained in all cases.
Improved imagery during this early period was, of course, the result of technical refinements made to the system, changes brought about by actual flight experience. Paul Heron gives us some examples.
One of the major problems we had to overcome was the ability to precisely locate the target material obtained from the system on the ground. To do that, we incorporated a stellar camera. Now, a stellar camera is nothing more than the name implies. It takes a picture of the star field. Knowing the fixed positions of the stars by triangulation of the stellar photograph, we can determine positively the position of the vehicle at the time the photograph was taken.
The original Gambit configuration had provided an average of 1,000 photographs or frames per mission, high-resolution imagery that had answered many questions posed by the intelligence community. To explain is Mr. Arthur Lundahl, the first director of the National Photographic Interpretation Center in Washington, D.C.
Well, the reaction to these new missions was electric. It was widespread and it was sustained. Here we were getting unequivocal technical intelligence on the whole Soviet military posture. And all through our country, from the presidents and the cabinet level people down to the individual intelligence analysts, there was great excitement. Many presidents had gross commentary to make. For example, one president said, "The value of the photography alone is worth more than the total cost of the whole U.S. space program."
Though the original Gambit system exceeded the initial specification for a 2-foot ground resolution, world events dictated that even higher quality imagery be obtained to meet national intelligence needs. General King describes for us the proposed specifications and procedures formulated in 1964 for such a new system to fulfill these requirements.
It also was apparent that the that the understanding that we now had of operating a high-resolution mission from space that would allow us to actually do this. And so there was an advanced program introduced which would provide a Eastman longer focal length camera. It would allow us to use the now clearly demonstrated stable Agena as a basic stabilization platform. A more powerful booster, the Titan 3B, had now become available, and we could provide the weight on orbit that we needed. And particularly, we could minimize the risk of returning the photography from orbit by using the now clearly demonstrated General Electric recovery vehicle.
Mr. Les Mitchell describes the major optical improvements which became operational in 1966.
The advanced Gambit camera payload is 5 feet in diameter. The weight budget is 3,400 pounds, and that includes the external skin and structure. The advanced Gambit optical system is much larger than the Gambit optical system. It has a focal length of 160 inches.
The advanced Gambit system also called for improvements to the Agena upper stage. Mr. Robert Powell of Lockheed describes these advances.
First was the implementation of the factory-to-pad concept, where the vehicle bypassed the missile assembly building, where previously servicing operations and checkout had been performed on prior Agena vehicles, further reducing the error and the chances for making mistakes and speeding pad operations. Was the idea of using test teams that would take a vehicle through system tests here at the factory, go with it to the pad and go through the pad operations with it there, then go up to the STC and support the on-orbit operations before coming back to the factory to pick up another vehicle and take it through those types of operations. Another first was program integrated acceptance testing, which significantly shortened the time at the Vandenberg launch base. Another very significant first in the program was the all-up vehicle thermal vacuum and acoustic testing. Finally, and most important, was the simple concept of using an interface suction between the payload and the Agena vehicle, and this became known as the roll joint, which will be discussed in more detail by Larry Jenkins.
A key element of the advanced Gambit design was to maintain Earth orientation while at the same time providing the versatility and agility of the payload to sweep to various places on the Earth's surface. That was accomplished by use of a roll joint, where the motion of the payload was compensated by a counter-rotating wheel inside the vehicle. This provided the tremendous versatility to acquire the rather dramatic coverage of the advanced Gambit system.
The first launch of the advanced Gambit took place on July 29, 1966, only 4 weeks later than the date originally established 2.5 years earlier. And to assure continued and uninterrupted coverage of denied areas, the final missions of the original Gambit system overlapped the early advanced Gambit flights. Paralleling the advanced camera payload were improvements in film technology. For example, on the third advanced Gambit flight in December 1966, a new film only 1.5 mil thick was used. Miss Judith Schwann, Assistant Director of Eastman Kodak Research Laboratories, describes the new thinner films.
It's not very often that we think about trying to improve the amount of information that we store on a volume basis. But in this program, that was a very necessary thing to do. We started this program coating the silver halide emulsions on a film support that was 2.5 mils thick. During the course of the program, we were able to thin that down to 1.5 mils and finally down to 1.2 mils. We were able to pack a lot more information in a given volume, and that meant many more frames per mission.
In the late 1960s, while our Apollo lunar exploration program moved confidently toward successful landings on the moon's surface, we acquired first-hand photographic evidence of a catastrophic launch pad accident at the Soviets' J-pad, an event which may have spelled failure for their manned lunar exploration program. In similar fashion, Gambit imagery was giving us detailed data on Soviet ICBM production and deployment. The increasing requirements of our intelligence agencies for coverage of a number of specific targets within Soviet areas gave impetus to continuing improvements. One was the incorporation of dual recovery vehicles, or buckets, starting in August of 1969. Again, Mr. Arthur Lundahl.
This meant if there were a crisis in the world, we could cut down one bucket and get the intelligence while it was urgently needed without aborting the mission, and at the same time leave the mission go on and load up the other buckets so that we got a full value for dollars spent. It was a huge step forward, and the community truly appreciated what this meant to the collection effort of the United States.
As the decade of the 60s drew to a close, the average number of frames per mission had reached about 9,000. Accompanying the continuing increases in coverage were steps taken to further improve image quality. Mr. Les Mitchell details one important advance in optical performance.
During the early 70s, another change was the incorporation of the R5 optical system. The change to the R5 optical system increased the focal length from 160 inches to 175 inches. This would increase the image size on the film. Overall, these improvements were expected to considerably improve the ground resolution of the imagery. And in fact, that occurred on the first R5 flight.
That flight in August 1971 included other innovations. Retired Air Force Colonel Lee Roberts, a former Gambit program director, explains.
During the history of the Gambit program, we made a number of evolutionary changes to the system. And among these were items such as the integrated secondary propulsion system and the hot gas control system. And we did a lot of thermal modifications so that we could fly the vehicle lower, using the rule of thumb that for every mile we got closer to the target, we improved the resolution a tenth of an inch. This also required that we modify and develop a new heat shield for the reentry vehicles so that they could be recovered from these new lower altitudes. In one flight, we actually took pictures at altitudes below 65 nautical miles.
Gambit progress was achieved in a series of evolutionary improvements. Typical of this was the ongoing optical improvement program at Kodak during the early 1970s.
Through continued improvements in film, optics, satellite control, satellite stability, the resolution of the advanced Gambit system was improved to of ground resolution. The use of lasers and interferometric testing of optical surfaces was a major factor. We developed ways to evaluate that interferometric data by computer and feed that information directly back to the people who were polishing the optics. These things all came together to yield optical systems with overall wavefront errors of less than 1/4 wavelength.
Strict dedication to image quality in manufacture, as well as in field operations, yielded the kind of data required for technical intelligence purposes and treaty verification.
The ever-improving image quality pushed the whole U.S. photo reconnaissance effort to the highest state of the art. We were able now to get dimensions on objects beyond anything we had ever been able to do before. And from these real dimensions, we could now tell very, very important things about our would-be adversaries. For example, if we looked in his submarine yards, This enabled us to tell where they might be better able to operate. It opened wide our operational concepts as to where we might have to confront them. And it gave us so much technical detail that we could actually go forth in the making of three-dimensional terrain, or in this case, submarine models, so that our operators could learn a great deal about the kinds of facilities that you would find at the launch site. It was a real big breakthrough for the whole intelligence community. It reminds me of an age-old expression. Archimedes once said, "Give me a place to stand and I'll move the world." The photo intelligence people equipped and working hand in hand with the engineers said, "Give us some accurate dimensions on our adversary's military equipment and we'll move the whole country into a whole new world of intelligence estimating," and we did.
In 1973, Gambit began to demonstrate routinely another system capability.
The Gambit's high-resolution cameras are able
Development of even finer grained emulsions and improved processing technology was pursued to record targets requiring exceptionally high resolution. The new emulsions, termed monodispersed, exhibited a finer and more uniform grain structure. This enabled higher magnifications of small areas of Gambit frames to achieve closer examination of target details. And to attain the highest possible resolution from these new films, viscous processing techniques were developed to provide dual gamma imagery that retained deep shadow detail while preventing loss of highlight detail. An appreciation of what current Gambit imagery means is outlined by Mr. John T. Hughes, Deputy Director for Defense Intelligence and Senior Intelligence Advisor to the Director of the Defense Intelligence Agency.
High-resolution Gambit imagery has provided the magic catalyst that has helped to demonstrate to U.S. leadership the true nature of Soviet growing capabilities. First, let's talk about Soviet ICBM silo construction and hardness. From this kind of evidence, the United States intelligence community in 1982 has ascribed hardnesses of these silos Let me now turn to Soviet intermediate range system developments and focus on the SS-20 system. There are many facets and aspects of the SS-20 system that we are attempting to understand. This manufacturing facility is designed for the production of components of the SS-20 in a tactical mode. This building has an outer yard with many of the components or chassis of the SS-20, which with the Gambit photography, we can clearly enlarge. Let me show you one of those buildings enlarged with equipment found nearby. This is SS-20 ground support equipment. These are transporter erector launchers, or TELs, that provide for the erection and firing of the missile when it's in the field. So with the satellite photography, we understood the basis for some of the Soviet equipment developments, and they provided the signatures for subsequent identification in the field. Let me turn to Soviet ground force developments. Let's discuss how Gambit high-resolution photography was used to detect and determine the status of a Soviet tank division which had been moved into Bulgan, Mongolia a few years back. This is a overview of the motor pool area where all the equipment is stored in the open. All the elements of a Soviet tank division displayed on this Gambit imagery of high quality. Not only could we see the complete layout with the coverage provided by the system, but we could take each segment and very carefully make counts and types of weapons determinations.
To provide the intelligence community with increased flexibility to attack certain problem targets, a second strip camera sharing the same optics with the standard 9-inch Gambit camera was incorporated. This added 3,000 more feet of film for special tasks. Mr. Tom Hanlon, Gambit program manager at Kodak, explains.
In the late 70s, we added the 9x5 camera system, which really means the addition of a 5-inch film system to operate simultaneously with the 9-inch film system. In fact, it can operate simultaneously or independently. Both are redundant. For example, that you can utilize a number of emulsions simultaneously, again, or independently, starting, of course, with the high-resolution, very high-quality black and white film. Add to that, on the other system, a very high-speed film, so as to be able to take photography where low sun angles apply, color, false color, or infrared, near-infrared films, all of which give added spectrum, if you will, capability in which to evaluate targets.
Though much emphasis has been placed on the evolution of system hardware in this history, the success of the Gambit system also has depended heavily on the satellite control procedures and techniques evolved by the Air Force industry team. Retired Air Force Colonel Ken Cavanis, at one time Deputy Director of Special Projects at the Sunnyvale Satellite Control Facility, recounts how targetry operations took form.
Remember in the early days, the idea was, once we were on orbit, turn the camera on, get as many targets as you can, because we really didn't realize or know how long we were going to be on orbit. 3 to 7 days, probably at the maximum. Today, with as many improvements been made, then it became very important to get with the users and find out the unique requirements you really have. What are the targets you really need, and are there anything we can do out here to help you? In the early days, as I mentioned, we were lucky to get 300 to 800 targets. Today, they're getting over 15,000 unique targets per mission. That's rather cost-effective. The other factor that they've been able to do out here, the other requirements would come in, and now we're looking at requirements that are based on resolution. What do you want the resolution of that target to be instead of just taking the target? Are there unique look angles you would like to see that particular target? Classic example of that was one of the first times we ever tried it was the Pachura radar. The intelligence community had never seen a certain face of that radar during its development. So the intelligence community, working with operations, said, can you get us that look? On the first attempt, we got the other side of the radar, which proved of great value to the intelligence community. It's this kind of interaction that has made this one of the most successful programs ever developed.
Today, Gambit is a complex system of great effectiveness and reliability. Its successful operation requires the closest cooperation between the Secretary of the Air Force Special Projects Office, the Satellite Control Facility, key contractor organizations, and launch personnel of the Western Test Range. To summarize how the overall capabilities of the system were achieved is Colonel Les McChristian, Gambit Program Director.
The history of the Gambit program has been one of continuing improvements throughout its life. For example, improvements in the quality of the film and the optics has already been discussed. Also, we've made dramatic improvements in the quantity of the frames that we're imaging, and also in the mission durations of the system itself. In terms of improved quality, as been previously discussed, we now have a system that's capable of imaging resolved distance photography. For example, on mission In terms of quantity, on Mission 51, we had 24,500 frames returned, satisfying over about 17,000 intelligence requirements. In terms of mission duration, we now have a system that is capable of flying up to 120 days mission duration. This allows us to wait out the weather, and on Mission 51, for example, we returned about 70% cloud-free imagery. In late 1977, after the flight of Vehicle 51, the Gambit program was designated as a backup system to the National Reconnaissance Program. In this role, we were tasked to not only provide a high-res mission, but also we made modifications to the system that allowed us to fly in the all-high search synoptic coverage mode. For example, we could continue to fly the all-high resolution mission at the 70 to 75 mile altitude, or we could fly the all-search synoptic coverage mode at 450 miles. Or we could fly a combination of high-resolution missions as well as a search mission in a total 120-day mission duration. This illustrates a pass of the Gambit system over the Middle East in the high-altitude search mode. On one pass, the Gambit system could take approximately 27,000 square nautical miles of photographic imagery, using only 11 feet of film in the system. The continuing improvements that have been made to the Gambit program over the years undoubtedly makes Gambit the highest quality, high-resolution photographic system in the world today.
Fire engine.
0, plus 1, 2, 3, 4, plus 5.
Marking S number 1, lift off the third S. 19, so on.
In a typical Gambit mission, military and contractor personnel at the Air Force Satellite Control Facility in Sunnyvale, California, begin receiving telemetry signals from the spacecraft shortly after launch. Within the first 2 passes over a tracking station, an initial orbit is plotted and appropriate corrections are transmitted to the satellite on a subsequent pass. On most passes, the spacecraft is in contact with one of the remote stations of the global tracking network. The stations, in turn, are linked electronically to the satellite control facility. There, individual targets are selected and given priority on computer software in terms of the highest probability of good weather. During a station pass, photographic commands are transmitted to the spacecraft within the 5 minutes or less that the vehicle is within range. These commands can be revised to fulfill mission requirements. As the Gambit mission progresses, photography of selected targets, whether monoscopic exposures or stereo pairs, is imaged with pinpoint accuracy. Focus, exposure, and image motion compensation are optimized by advanced satellite control procedures. 2 orbits before the recovery pass, the spacecraft is commanded to yaw 180 degrees and is pitched down to approximately 60 degrees. The re-entry vehicle is separated, spin stabilized, the retromotor is fired, and deorbited. After the capsule has decelerated sufficiently, the main chute deploys. Recovery aircraft catch the descending parachute and its capsule using a special air recovery device. Once caught, the capsule is reeled into the aircraft and flown back to Hawaii. After a swift air journey, the satellite recovery vehicle arrives at the film processing facility. There it is placed in a special holding frame to align it with the pre-splice complex, a device used to rewind the exposed film to the as-flown or heads-out position. During rewinding, the film is carefully inspected for any defects that might create processing problems. Following rewinding, a light, tight cover is placed over the take-up spool dolly for transport to the processor room. Here, processors can develop continuously any length roll of original negative film. The computer-monitored processing cycle consists of 6 steps, starting with a static viscous layer development and ending with film drying. Following processing, duplicates are developed on a viscous processor operating at approximately 100 feet per minute. All critical processing parameters are monitored from a central console area that controls 4 processors. The processing facility maintains a capability of producing thousands of linear feet of quality black and white duplicates each 24-hour day. Duplication is not complete until the product passes physical and photographic quality inspections to assure that optimum print quality has been achieved. Following inspection, copies are shipped to the various intelligence agencies. Subsequently, all original Gambit negatives are sent to Washington, D.C. for permanent archiving at the National Photographic Interpretation Center. The center's director, Mr. R.P. Hazard, offers his evaluation of Gambit imagery.
High resolution has been the hallmark of the Gambit system. Here at INPIC, the imaging analyst must examine an image to determine the presence or absence of the item of interest, and once having found it, make a careful analysis to determine its detailed characteristics, to include any changes that might have occurred. During this process, the analyst makes use of a host of reference material, such as previous photography, previous readouts of that photography, handheld photography, and other technical intelligence data. Often the analyst will require that a series of precision measurements be made. In such cases, a photogrammetrist, using specially designed comparators, which are supported by a complex computer program, will extract a highly accurate measurement. In this regard, Gambit provides the quality of imagery necessary for the most accurate measurements.
The accomplishments of the Gambit system are summarized by Major General John E. Culpa, Director of the Secretary of the Air Force Special Projects Office.
The Gambit system was devised to meet an urgent national need. The Soviet Union, in the latter part of the 1959 time period, had demonstrated a capability to build and accurately control an ICBM. Earlier, they had detonated a thermonuclear device. Our country had to know the extent of Soviet deployment and the exact capability of these new terrible weapons. It devised a 2-satellite system, the Corona to search and locate Soviet development and site deployments, and the Gambit to then focus in and get the technical detail. That required a system of very high quality. I can recall early in the Gambit program, General Greer commenting on the fact that, and half in jest, but not entirely because he was serious, he'd comment on the fact that he would like to see needless to say, it can photograph a submarine or an aircraft or a tank, tell minor changes, tell improvements, and from accurate mensuration or measurement of distances can derive performance. This accomplishment has been a result of a team effort, a team of government people and contractor people, of scientists, of engineers, of operators, of photo interpreters, and of intelligence analysts. Not only has the Gambit provided high-quality technical information, but because of the flexibility of the system, we have been able to develop a capability of taking pictures. And more recently, we've developed a capability which allows us to fly at higher altitudes, therefore performing a backup search function. Through 2 turbulent decades, Gambit has provided high-quality, reliable technical information.
This information has allowed our country to make some of its most critical decisions involving our own force structures and performances required. Decisions that may influence and have influenced diplomatic moves on the part of our country. And possibly most important, it has allowed us to enter into treaty negotiations with the Soviets because we now had a mechanism to monitor these treaties. In this manner, Gambit has been a most significant contributor to our world stability.
As our secret sentry in space, Gambit has provided the clear and constant vigilance our nation has required. The piercing gaze of Gambit has demonstrated once again the preeminence of American space technology. But far more important, as the eye of the eagle, Gambit is helping to guard us from those who would destroy our lives and liberties, contributing immeasurably to the preservation of peace.